Okay, in this video we're going to talk about the different types of organic reactions, and I have a whole list of them here. And the first type of reaction that we're going to talk about is a combustion reaction. And combustion reactions are always where you take an organic fuel, add oxygen to it, and you're going to get carbon dioxide, water, and heat. And because you get this heat, we consider it an exothermic reaction. Now, you can find some examples of combustion reactions on table I. So I'm going to go ahead and grab table I for us. And so here's table I. You can see that on the top of table I, right here, and these first 6 all start with an organic compound, add oxygen, produces carbon dioxide and water, just like we have up here in this example. Okay? You can also look at the bottom of table I, and you're going to see this that says a minus sign indicates an exothermic reaction. Exothermic because they have a negative delta H. All of them have a negative delta H. Let's get a pen, right? And they're all giving off heat. That's what fire does. It gives off heat, and so it is an exothermic reaction. The way we recognize these is by looking at the products. Let's find it right here. And we see that they're always going to be carbon dioxide and water. The next type of reaction requires that we have a hydrogen atom removed from an alkane and we substitute it with a halogen. Okay, so let me show you how that works. So what I did was I went ahead and drew a saturated hydrocarbon. Hydrocarbon because it's all carbons and hydrogens, saturated because it has all single bonds, and I'm going to add to that, or react with it, a bromine. Now, in order for the bromine to attach, there's no room. So remember, this bromine is 2 BRs. It's a BR and it's another BR. Okay, so in order for that to attach, I'm going to have to take a hydrogen off. So let's get an eraser. Let's take a hydrogen off. Come on, eraser, you can do this. Okay, and we're going to take one of these bromines and we're going to place that bromine on there. Now the hydrogen that came off is going to hook up with the bromine that is left. It's substituted in for a hydrogen. So one hydrogen came out, one bromine went in, and we end up with 2 products, and one of those products is a halogen, and we have, in this case, hydrobromic acid. Okay, 2 products is your key, right? Here's 2, here's 2, here's 2. Now in this reaction, an addition reaction, we now have an unsaturated hydrocarbon. So we have to have something that has a double or a triple bond in it. So I'm going to draw the one with the double bond in it, and we're going to add the bromine again. But now we have a double bond. So I'm just going to draw that on this side so you can see. And so this right here is the same as this. I'm going to show you what happens. We're going to take this double bond and we're going to break it. So now it's a single bond. And because of that, this carbon only has 3 bonds left. It needs another one because remember, every carbon needs 4 bonds around it. So I'm going to make available a 4th bond around each one of those carbons. Now this bromine says, woohoo, there's space for me. So he goes over and both bromines add, addition reaction, to that ethene, which turned into an ethane. So this becomes 2 dibromo ethane. Ethane because you have 2 carbons in your parent chain. Di because there's 2 bromines. Bromo because they're bromines, and they are on carbon number 1 and carbon number 2. Alright, in a fermentation reaction, we're going to take a sugar. In this case, the sugar is glucose, here, right there, glucose, and some sort of enzymes. A lot of time they will say yeast above the arrow, and you will produce alcohol and carbon dioxide. And this is how they produce sparkling wine, champagne, beer, all that stuff. They ferment some sort of sugar. Sugar is coming from the grapes or the barley or the hops. Then there's yeast that is growing naturally on those grapes, and then you ferment it and you get alcohol and CO2. So this is just an equation that you just kind of have to commit to memory. You have to know if you start out with sugar and you end up with alcohol, it is a fermentation reaction. All right, an esterification reaction. This is a big one. This is one they like to ask about. Well, remember Aunt Esther up here. Let's get a pen that writes, actually. Aunt Esther, she takes antacids. Okay, antacids and alcohol. And that is a way to remember that when you are making an ester, that's what esterification is, you need an acid and an alcohol. So let's say I draw propanoic acid, and it's propanoic acid because, let's get a pointer here, there is the acid functional group right here at the end. And then what I'm going to do is I'm going to draw a alcohol over here. It's going to draw it backwards just so you can see what actually happens. And if I take a water out, so I take an H, and an O, that's an H2O or an HOH. And if I remove that, this O right here is going to join up with the carbon. So it's going to end up looking like this. You're going to have a C, a C, a C, and a double bonded O. That is this. Let me get a highlighter so I can show you. That's a very, very skinny highlighter. That's this part. Okay, so I'll highlight it in pink. And then we're going to take this, which I'll highlight in green. No, green's not a good color to do that in. Yellow, with that O. So you see how it has two C's. Bah. Get yourself a pen that writes, Kaufman. All right, so you got two C's, and you've got an O there. Don't forget those little H's. Those are on there too. And this O that's right here, that O hooked up with this C. That O hooked up with this C. So we'll put a little line between it because there's now a bond there. And now, get that green highlighter again. Oh, sorry, it was yellow, but you get the idea. That right there is the alcohol portion, and the pink was the acid portion. Now, you can see, and I'm going to get a pen. Let's see, let's take it. What color do we want? Blue is good. You can see that the functional group is right here now, and that's the ester functional group. Ester functional group, right there in the middle. So I'm going to squeeze that down if I can. Put that on the side, and I want to try one more, and I want to go the opposite way this time. I want to take an ester. All right, so I drew an ester here for us, and the first thing we're going to do is we're going to name this ester. Now, if you recall, when we're naming esters, we always want to name this side first. So that side is methyl, because it only has one carbon in it. And then we're going to name the other side, which actually happens to have 5 carbons in it, so that's pent, and we end our esters in anoate, so it's methyl pentanoate. Now, once we have the name, there's a couple things they can do here. They could actually give you an ester and ask you, I just wanted to get rid of that yellow. Oh, sorry, the name went away, but you'll remember it's methyl pentanoate. They might ask you what acid or what alcohol was used to make this ester. So what we're going to do is we're going to split the ester right between the O's. And the way I remember it is I think of these as little eyeballs, right? And there's Aunt Esther's eyeballs. See them? Those are not bonds, those are eyelashes. Let me get rid of them so you don't get confused. Okay, so we're going to punch Aunt Esther right between the eyes. That's not really a very nice thing to do, but that's the way we're going to remember it. And when we split that right between the eyes, the pent portion becomes the acid. This is the acid. It has the double bonded O, and this is the alcohol side. And you can see that it had 5, so it was pentanoic acid. And then the alcohol had 1, so it was methanol, because alcohols end in an ol and acids end in an oic. All right, so you should be able to go both ways. You should be able to take the acid and the alcohol and make the ester, and you need to be able to take the ester and break it down into the acid and the alcohol. The hardest part is remembering which side is which. This side is the alcohol side, and this side is the acid side. The acid, because of the functional group C double bond OOH, will always have that double bond right there. All right, number 6, chemical reaction number 6 is a pretty easy one. You do not need to memorize, or let's get a different color or a highlighter here. You do not need to memorize this. You do not need to memorize this stuff over here, but you do need to know the word equation for saponification, and that is a fat, sometimes they call it a lipid, okay, and a strong base, which they generally use sodium hydroxide, will give you soap and glycerol. Oops, glycerol. There you go. Okay, you don't need to know the formulas for them, but you should recognize that glycerol is a trihydroxy alcohol. It's the only alcohol or trihydroxy alcohol that they will ever give you, and it looks like that. Okay, it's trihydroxy because there are 3 hydroxyl groups, and they are right here. Oops, 1, 2, 3. 1, 2, 3. How many licks does it take to get to the center of the Tootsie Pop? 1, 2, 3. Crunch. Okay, I digress. All right, any questions on that one? I think we're good to go. That's an easy one. All right, number 7 and number 8 are polymerization reactions. And a polymerization reaction is simply just making a molecule, a very large molecule, that is joined, that is a bunch of units, of simple units joined together. And those simple units are called monomers. So if it's a repeating pattern of molecules joined together, either by withdrawing a water molecule, that's how we get the word condensation. We take a water molecule out. I'm going to show you that in a second. Or in the next slide, which I'll show you, breaking a double bond or a triple bond, that's addition polymerization. So both of them are basically the same. We're making a molecule, a bigger molecule, by joining repeated units. So I'm going to pause for a second. I'm going to draw a glucose molecule. Okay, I drew a glucose molecule. Let's erase that for a second. I drew a glucose molecule, and let me make it bigger so that you can see it. All right, it looks pretty complicated, right? But simply put, it's just 6 carbons, and here they are. 1, 2, 3, 4, 5, 6, 12 hydrogens, you can count them all the way around there, and 6 oxygens. 1, 2, 3, 4, 5, and 6. So this is just a glucose molecule, C6H12O6. And with this glucose molecule, oops, I lost my C6. Something gets bigger, something else gets smaller, who knows? Okay. Here's another glucose molecule. I'm going to put it right next to it. So there's 2 identical. Now each one of these is a monomer. Monomer because they are a single unit. I'm just going to erase this because it's in our way. Okay. Monomer because it's a single unit. I can move them independently. That's a monomer and that's a monomer. When these guys get close enough to each other, we can remove a water, just like we did with the other example when we did esterification and we removed the water. Let me get a highlighter. If I take an OH and an H from there, that O that is left is going to join this monomer, the one right here, and this monomer together. So let me draw that for you. Okay, so what you can see here is I removed a water, I took the OH and the H, and now there is a naked O right there. Let me show you where it is. It's right there, right? Right there, right there. I kind of flip-flopped them, so hopefully you don't get too confused. And then this guy's going to come in and is going to attach to that O. So this is the new bond right here. Let's see if I can do it with a highlighter. Be easier for you to see. Okay, so the H and the OH come out. I'll draw them in blue. H and OH come out, and one O was left. That's this O, and that's the same O right there. So I hope that's condensation polymerization. Repeating units of monomers joined together to make a polymer. Poly meaning many. It's that polymer up there, monomers. And what are these things? Well, they're things like proteins, starches, like if I put another glucose after this and worked with this OH, it would become a very long chain of glucose molecules. It would be a complex carbohydrate. It would be a starch. Okay, so here's another one up here. They give you an example of polyester. The word poly is already in there, and it's an ester that is going to be your repeating unit. Anytime you have repeating units, it is a polymer. All right, on the next page here, you have addition polymerization, and this one is the same basic idea. You have monomers, but now they are made from unsaturated monomers, meaning it has to have a double or a triple bond. So the example they give you is C double bond C, which is an ethene molecule, and that ethene molecule might show that you have N numbers of them. Now this N is telling you you have that many ethene molecules. And then what will happen is that bond will break. This double bond right here will break and become a single bond. And I'm going to draw these black lines again. And so you'll notice now that you only have 1, 2, 3 bonds coming out of each carbon. 1, 2, 3 bonds coming out of each carbon. So you know, because I've told you, that you need 4. So we're going to put another line around that carbon. That's the new bond that was formed. And that new bond allows another carbon, another ethane molecule to form. So what they'll do is they'll actually put this in parentheses, and they'll put an N on the bottom here. That N and this N are the same. It's saying that you have N number of ethenes, and then what happens is the bond breaks and it becomes a subscript saying that they're all connected to each other now, and you have a polymer. Polymer meaning many repeating units of the same thing. Alright, so that pretty much wraps up your organic reactions. I know it's a lot to digest, but that's why I made this video. So if you need to go over any of them, or if you have any